Hey guys, welcome back to On the Spot STEM, and today we will be tackling MIT Integration B qualifying exam given in January 2019. Specifically, we will be looking at problems 1 through 10. Leave a like, comment down below, subscribe if you're new, and let us know if you're interested in seeing the solutions to problems 11 through 20 as well. The timestamp for each of the 10 individual problems will be given down in the description below, as well as the PDF to the answers and to the problems.
Number 1 reads, what is the integral from 0 to 2 pi of tangent of cosine of x dx? Now the problem with this integral is that there are no clear, clever substitutions right off the bat. If I try letting u equals cosine of x, then I run into problems and dead ends with du equals negative sine x dx. But here's what we can do. We can start by trying to draw a graph. Notice that the maximum of cosine of x is going to be 1, which means the point on this graph is going to be tangent of 1. Which we'll call this the y max. And then the lowest cosine of x can never be is negative 1, so then the minimum here will be tangent of negative 1. Now let's start off by trying to plot some zeros. We quickly see that pi over 2 is going to be 0. And remember, the way we get this is that tangent is nothing more than sine of cosine of x over cosine of x. So we just need to let this top part be equal to 0. And that's how we can see the patterns that follow through. So pi over 2 becomes 0. And then I see that at x equals 0, we start off at tangent of 1. At x equals pi over 2, we go to 0. At x equals pi, we go to negative 1. And then at 3 pi over 2, we go to 0. And then at 2 pi, we see quickly that we are at tangent of 1. So then the graph looks something like this. So we want the integral of this function. And all we have to note is that if I were to draw this little dotted line right here, there's symmetry. This area is going to be equal to this area, and this area is going to be equal to this area. And so the integral, the answer is just going to be 0. Number 2 reads, what is the improper integral of x plus 1 divided by quantity x times x plus log x dx? Now we start off this problem with the clever u substitution. Let u equal x plus log x. Because this is obviously the nastier of the two terms in the denominator. So that's the motivation. Then we find that du equals 1 plus 1 over x dx. Which is also the same thing as saying du equals 1 plus x over x dx. Which means we can deduce from here that x times x plus 1 du equals dx. So now we can substitute this back into our integral up here. This integral is going to be integral of x plus 1 times x times 1 over x plus log x dx. And so when I substitute everything I need, I'm going to have x plus 1 over x times 1 over u times, and for dx we see through this equation that dx is x over x plus 1 dx. Du. And so this term cancels out with this term, so I'm left with integral of 1 over u du, which we know is just ln of u. So the answer is just ln x plus log x. Problem 3 reads, what is the integral of e to the power of x plus e to the power of x plus e to the power of x minus e to the power of x dx? Now, there's obviously one important thing to know, is in math, if I have a to the power of b plus c, that is the same thing as a to the power of b times a to the power of c. And this will be the key to solving this problem. So let's rewrite this integral as the integral of e to the power of x times e to the power of e to the power of x, because this term then becomes x plus e to the power of x, which is the b plus c, plus e to the power of x times e to the power of negative e to the power of x dx. Now that's kind of a ugly integral, but yeah, now it looks cuter. So then I see that there's a lot of e to the power of x's everywhere. So that motivates me to say, let u equal e to the power of x. And then this nicely becomes du equals e to the power of x dx, which means du over e to the power of x equals dx. Now, we can resubstitute. We have this integral that now becomes integral of u times e to the power of u plus u times e to the power of negative u times, and the dx becomes du over e to the x, du over e to the x. But e to the x is just u, as we showed by substitution, which means we can cancel out the u from these two products, because a times b plus a times c divided by a is going to be b plus c, because, just commutative property. So this integral then becomes integral of e to the u plus e to the negative u du, which is e to the u minus e to the negative u, and now we just have to substitute the u back for e to the power of x. So this is equal to e to the x minus e to the negative e to the x, and that is the answer. Wow, that was a lot of e's and x's. Number 4 reads, what is the integral from negative 1/2 to 1/2 of dx over 1 minus x squared? And the fastest thing to note is that 1 minus x squared equals 1 minus x times 1 plus x. So I can rewrite this whole 1 over 1 minus x squared equals a over 1 minus x plus b over 1 plus x. And this algebra will yield that a equals b equals 1/2. And if you really want to do it, it's just like Calc BC, partial fraction decomposition. All you have to do is rewrite a times 1 plus x plus b times 1 minus x equals 1. So I see ax minus bx has to be 0 since there's no x term, so a equals b. And then I have a plus b equals 1, so it's just 1/2 each. So then I'm essentially integrating 1 over 2 times 1 minus x plus 1 over 2 times 1 plus x, and I'm just integrating this. And so this integral actually becomes 1/2 log of 2 plus 2x minus 1/2 log 2 minus 2x. And the reason this is, obviously there's 1/2 is because in the chain rule this 2x yields a 2 on the top, so I need a 1/2 on the to cancel out that 2 on the top. And this is minus because it's a negative 2x, and so I need to get rid of the negative sign, so I'm doing negative 1/2. And so now I can just factor out a 1/2. I'll just factor it out and then get rid of this. And so now I want to integrate, or I'm evaluating this expression, 1/2 log 2 plus 2x minus log 2 minus 2x, and that's evaluating from x equals negative 1/2 to x equals 1/2. And so when I first plug in 1/2, I see that I'm going to have log of 3 minus log of 1, which is just 0. And that's minus, and I put in x equals negative 1/2. So that's log of 0, which is also 0, minus log of 3. So I have log of 3 minus log of 3, so I'm just subtracting by negative, which is adding the positive. But then I have to multiply 1/2, because this 1/2 carries down here. So then now I have 1/2 times 2 times log 3, which is equal to log 3. Number 5. Number 5 was honestly kind of a weird problem. There was integral from 0 to 2 of 2 to the power of log x dx. And in the first 10, this was probably one of the problems I struggled with a little bit more. You probably have a very fast solution. If you do, comment down below. But this was my rather boring solution, but it was fun to play around with. And so basically, there's 2 key observations. I note that the derivative of 2 to the x, is 2 to the x ln 2. This is basic calculus BC. And then the integral of 2 to the x, which is going to be the contrary, is 2 to the x over dx, good practice, equals ln 2 to the x over ln 2. So this is the motivation we proceed with. Let's just say, what's the derivative of 2 to the log x? Well, that's going to be 2 to the log x, ln 2, and then chain rule on the exponent times 1 over x. So I see there's going to be this 1 over x that I would want to get rid of. So naturally, I'm motivated to multiply it by x. So now, let's say instead we have x times 2 to the log x over log 2. Now let's find the derivative of this term. So essentially what we're doing in this problem solving process that I want you to think of is we're working backwards. We're trying to find what the antiderivative is and try to work our way to this expression of 2 to the log x so that we can easily integrate it. So now my motivation to multiply by x is to cancel out this 1 over x. And then I have this divided by log 2 on the bottom because I want to get rid of this ln 2. Ln log I'm going to use pretty fluidly. This integration B uses log, but normally I use ln, but I hope that doesn't confuse you too much. So I'm multiplying by x and dividing by log 2 to try to get rid of these two terms. So now let's take the derivative. But the thing on the top is now I have a chain rule. And so chain rule tells me that what's going to happen now is that the top is going to become 1. Or actually, I'll just start off without integrating x. So I have x times 2 to the log x times log 2 times 1 over x. And then this is plus, if I say, now this time I take f prime on x, 2 to the log x, all divided by log 2. And so this expression, I notice that the 1 over x and the x cancel. So this then becomes 2 to the log x times log 2 plus 2 to the log x over log 2. And so what happens now is that I can factor this right here into 2 to the log x times log 2 plus 1 divided by log 2. But here's the thing that I note. I want this term right here to cancel to yield me just 2 to the log x as desired right here in the original problem statement. That's what I want. But I can just add 1 on the denominator because it's a constant. And through all these derivatives here, note that the bottom is always going to be log 2 and it's not going to change. So this cancels. So essentially, I found the antiderivative of the function to be x times 2 to the log x over 1 plus log 2. That's the antiderivative. The bottom will stay the same, and the numerator will be 2 to the log x times log 2 plus 1 the quantity, which cancels into 2 to the log x, as we've shown. And I have to evaluate this for x equals 0 to x equals 2. At x equals 0, is it going to be 0 times log 0 on the top, which is just going to be 0. So I only really need to evaluate for x equals 2. And for x equals 2, I get 2 times 2 times 2 to the power of log 2 over, oh wait, this doesn't show on the camera screen. I'll move it over here. If I evaluate, I get 2 times 2 to the power of log 2 over 1 plus log 2. And that is the solution to this problem. And number 6 reads, what is the integral from negative 2 pi to 2 pi of quantity cosine 3x plus sine 2x times quantity negative sine 2019x plus cosine 3x dx? And at first, it seems dry. There's really no place to start. But let's start off by expanding these terms. Or let's expand the product at least. So then when I expand the product, I get negative cosine 3x sine 2019x plus cosine squared 3x minus sine 2x sine 2019x plus sine 2x cosine 3x. And now here's the thing that I should note. It's that if I multiply an odd function by an even function, I'm going to have an odd function. And if I take an integral of an odd function, integral of, let's say, O of x or some odd function from negative a to a is going to be 0 because of the symmetry. Or like not symmetry, but the rotational symmetry. And so I see right here that this term is going to become 0, and this term is going to become 0 because cosine is an even function, sine is an odd function. So when I multiply them, I'm going to get an odd function, which means by this integration, it's going to be 0. Now, I see that cosine squared 3x, there's really nothing I can do for another parity test. In the parity, we're just testing the odd and even. Now let's look at negative sine 2x and sine 2019x. Let's just ignore the negative sign for now, or we'll just consider it, right? So if I want to find negative sine 2x, sine 2019x, I'm going to use a formula called product to sum, where I have trigonometric identities, where I have sine A times sine B. And I can rewrite that as a sum of two cosine terms, actually. And so this is actually going to be equal to negative 1/2 times the quantity cosine 2019x minus 2x minus cosine 2019x plus 2x. And so this, if anything, is negative 1/2 times the integral of cosine of 2017x minus cosine 2021x. But here's the catch, right? If I integrate cosine, I'm gonna have sine, and we know sine is an odd function. So if I'm evaluating this from negative 2 pi to 2 pi, this is always going to be 0, right? Because cosine will go to sine, and sine's an odd function. So this is going to be 0. So all I'm left with is this term. So essentially, the problem boils down to integral from negative 2 pi to 2 pi of cosine squared 3x, and the identity dx. And the identity we need to know for this problem is actually cosine 2x equals 2 cosine squared x minus 1, which means cosine squared x equals cosine 2x plus 1 all divided by 2. And I can rewrite this instead of x. In this case, I have a 3x. So I'm going to be left with the integral from negative 2 pi to 2 pi of cosine of 6x plus 1 divided by 2. I'll just move the 2 to outside this integral, so it's 1/2, and then dx. So this evaluates to 1/2 times, and when I take the integral, I get 1/6 sine 6x plus x. I should note that the 1 is outside the cosine. So I have that evaluated from negative 2 pi to 2 pi. And I see that when I put in 2 pi, I'm going to be left, I see that the sine term is going to become sine of 12 pi, which is the same thing as sine of 2 pi, which is 0. So then that's going to be just 2 pi, 1/2 times 2 pi. And I plug in negative 2 pi minus negative 2 pi because so it becomes plus plus, because negative 2 pi, sine negative 12 pi is also 0. So this becomes 1/2 of 4 pi, which is equal to 2 pi. And that's how you solve this problem. Number 7. The scariest yet easiest problem on the test. Integral cosine x times cosine sine x times cosine sine x dx. Now this problem looks pretty scary, but it's actually killed by u substitution. Believe it or not, this cosine sine x term looks the most intimidating. So our motivation is to let u equal sine x. Right, which means du becomes cosine of sine x times cosine x by the chain rule dx. Right, and from there I see that du over cosine sine x times cosine x equals dx. So now this integral here becomes integral of u, which is cosine of u, times, and then when I see this dx term, cosine sine x times cosine x is this term right here. So this cancels with that. So in fact, it's just integral of cosine u du, which is sine of u, which is equal to sine x. And that's all there is to this problem. Number 8 reads integral from 0 to infinity of e to the negative 2019 over 4t squared, all divided by t squared dt. Easily, in my opinion, the hardest problem out of the first 10. The most challenging for me, at least. You may find it different. So the first step is to note that negative 2019 over 4t squared can be rewritten as negative 2019 over 4 times 1 over t squared. 1 over t squared. So I'm going to say let u equal 1 over t. Du is equal to negative 1 over t squared dt. So negative t squared du equals dt. And so I'm going to substitute this back here. And note that when I u sub 1 over t, the bounds are going to flip because 1 over infinity pretty much approaches 0. So it's going to be integral from infinity to 0 of e to the negative 2019 over 4 times u squared divided by t squared times negative t squared du. So these t squares cancel. And this negative, I can just put this in the front. And as we remember from calculus, like BC or AB, if you have a negative, it just flips the bounds again. So this is essentially integral from 0 to infinity of e to the negative 2019 over 4 u squared du. And this is actually what's called a Gaussian integral. And solving this is a little tedious, but luckily for us, there's actually a generalized formula, which is for the Gaussian integral, is going to be of this form. It's pretty much of the form e to the power of, like x squared dx. And there's a generalized solution which says integral from negative infinity to infinity of e to the negative a times quantity x plus b squared dx equals square root of pi over a. So this formula is what we're going to use here. But in this case, it's even. The graph of e to the x squared is going to look something like this, with the peak right here. So it's even. So I can just say, in the problem here, 0 to infinity. So if I make this 0 to infinity, it's going to become this expression divided by 2. Then we can see that pretty simply. And based on this expression right here, we have a equals 2019 over 4. and b equals 0, but the b term doesn't matter in the integral. So if I integrate this, it's going to be square root of pi over 2019 over 4 divided by 2. And so this integral flips, so I have this is equal to 4 pi over 2019 square root that divided by 2. And then so this is just square root of 4 times, I can rewrite this even better as square root of 4 times square root pi times square root 2019 all divided by 2. And so square root 4 is just 2. So this is going to be 2 root pi over 2019 divided by 2. The 2's cancel. So this is equal to square root of pi over 2019. That's it to this problem. Number 9 reads, what is the integral of sine of quantity square root x dx? And the motivation is another common u substitution. So let u equal square root of x, which means du equals 1 over 2 root x dx. So 2 root x du equals dx. But no root x is u. So this is literally just 2u du equals dx. So then this right here becomes integral of sine of u times 2u du. And if anything, this is just a simple integration by parts. And if you watch our tabular method, which I recommend, and I'll probably put the link down below in the description, you should check it out, makes this integration really simple. So I'm integrating 2u sine u du. So I have the sine column, f prime column, integral g column. So I start with the plus sign, 2u sine u minus plus 2, 0. And this becomes negative cosine u and then negative sine u. So I take it in this order. So I'm left with the integral as negative 2u cosine u plus 2 sine u. That is our integral, and we're evaluating this. No. This is the integral. There's no bounds. I just realized. So I substitute back in for u, and I say I have negative 2 square root x cosine square root x plus 2 sine square root x. And that's all there is to number 9. Number 10 reads, what is the integral from 0 to 1 of square root of x divided by 1 plus x dx? Now, this seems a little annoying. Try substituting on the bottom, the denominator, but to no avail, we have no success. But this time, let's try letting u equal square root of x, which means in the same example as the previous problem, or in number 9, we see that we have du equals 1 over 2 square root x dx, which is 2 square root x du dx, which is the same thing as saying 2u du equals dx. And yeah, the way behind that is because then this moves over here to 2 square root x, and the square root of x is just u, so it's 2u du equals dx. So now I rewrite the integral, and I see it's the bound. The first thing to note is always check the bounds, and the bounds don't change because u equals square root of x, and square root of 0 is 0, and square root of 1 is just 1. So 0 to 1 of u plus 1 u over 1 plus u squared times 2u du. I'll move the 2 in here to the front, so then I have 2 times integral from 0 to 1 of u squared over 1 plus u squared du. And now here comes the most overpowered formula in math, which is u squared equals u squared plus 1 minus 1. Now, you're probably laughing. You're like, wow, you don't say, or wow, you're so funny, or you think you're funny, but you're not. But in fact, this actually destroys the problem, because if I substitute this for this u squared here, I'll have u squared plus 1 minus 1 over 1 plus u squared, which I can break into fractions as u squared plus 1 over 1 plus u squared minus 1 over 1 plus u squared. And if anything, this right here becomes 1. And I have 1 minus 1 over 1 plus u squared. But essentially, this is super easy because I know the integral to both of these. Integral of u squared of 1 minus 1 over 1 plus u squared is going to be u minus tan inverse of u. And this I'm essentially evaluating from 0 to 1. And then I have to multiply by 2 at the end. I have to remember that. So when I plug in 1, I have just u is 1. So 1 minus tangent inverse of 1 is pi over 4. and then minus 0 minus, and then tangent inverse of 0 is just 0 because tan 0 is 0. So then I'm left with 2 times 1 minus pi over 4. So the answer to this question is 2 minus pi over 2.